Listen to part of a lecture in an environmental science class.
Okay, so we've been talking about theories that deal with the effects of human activity on the climate. But today I'd like to talk a little bit about other theories that can explain variations in climate. And one of the best known is called the Milankovitch hypothesis. Now, what the Milankovitch hypothesis is about, it says that variations in Earth's movements, specifically in its orbit around the sun, these variations lead to differences in the amount of solar energy that reaches Earth. And it's these differences in the amount of energy that's reaching Earth from the sun, it's what causes variations in Earth's climate. Okay, a lot of people think of Earth's orbit around the sun as being perfectly circular, as smooth and as regular as, say, the way the hands move on a well-made watch. But it just doesn't work that way. You're probably aware that the Earth's orbit around the sun, it's not shaped like a perfect circle. It's more of an oval. It's elliptical. But the shape of this orbit isn't consistent. It varies over time, over a period of about 100,000 years. Sometimes it's a little more circular. Sometimes it's more elliptical. And when Earth's orbit is more elliptical, Earth is actually closer to the sun during part of the year, which makes Earth, and in particular the northern hemisphere, warmer. And why is that important? Well, because most of the planet's glaciers are in the northern hemisphere. And if it gets too warm, then glaciers will stop forming. And we already talked about how that affects Earth's overall temperature. The second movement involved in the hypothesis has to do with axial tilt, the tilt of Earth's axis, that imaginary pole that runs through the center of the Earth. And depending on the angle it tilts at, the seasons can be more or less severe. It makes winters cooler and summers warmer, or what some might say it's doing now, it makes summers less hot, and more importantly, the winters less cold, which, just like what I mentioned before, can also prevent glaciers from forming, or cause them to melt. There's a third movement the hypothesis covers called precession. Precession basically is the change in the direction of Earth's axis of rotation. It would take me 1,000,000 years to explain even just the basics of this movement, as precession is quite complex. And all these details are way beyond our scope. What's important for you to understand is that these three movements, while they're cyclical and they work together to produce complex but regular variations in Earth's climate, and lead to the growth or decline of glaciers. Now, when Milankovitch first proposed this theory in the 1920s, many of his colleagues were skeptical. Milankovitch didn't have any proof. Actually, there wouldn't be any evidence to support his hypothesis until the 1970s, when oceanographers were able to drill deep into the seafloor and collect samples which were then analyzed by geologists. And from these samples, they were able to put together a history of ocean temperatures going back hundreds of thousands of years. And this showed that Earth's climate had changed pretty much the way Milankovitch's hypothesis suggested it would. So this evidence was pretty strong support for the Milankovitch hypothesis. And by the 1980s, most people accepted this theory. However, in the late 1980s, some scientists were exploring Devil's Hole, which is basically an extensive water-filled cave far from the ocean in Nevada in the western United States. Over millions of years, groundwater left deposits of a mineral called calcite on the rock within Devil's Hole. And by studying these calcite deposits, we could determine the climate conditions, the temperatures, over the last 500,000 years. Well, the Devil's Hole findings contradicted the ones obtained during the 1970s. So basically, the question was, were the ages of one or both of the samples wrong? Or were scientists misunderstanding the significance of the evidence? Well, in the 1990s, a new study was done on the two samples, and the ocean floor samples were found to be correct, as were the samples from Devil's Hole. And now it's generally believed that the samples from Devil's Hole correspond to variations in local climate in the western United States, rather than global climate changes.